we think about a car moving down the road, it may seem simple from the outside. You press the accelerator, and the vehicle moves forward. But behind that movement is a complex system of components working together to convert fuel into motion. In this model, we can see the complete drivetrain system of a vehicle. It includes the engine, clutch, gearbox, drive shaft, differential, axle shafts, and wheels. Each component plays a specific role in transferring power from the engine all the way to the road. Let's start with the engine. The engine is the primary source of power in the vehicle. Inside the engine, fuel is burned to create controlled explosions that push the pistons up and down. This motion is converted into rotational movement by the crankshaft. This rotational force is sent to the gearbox in what is known as transmission. Before power reaches the gearbox, it passes through the clutch. The clutch acts as a temporary connection between the engine and the transmission. Once power enters the gearbox, different gear combinations can be selected. Lower gears provide more torque, which helps the vehicle start moving and climb hills. Higher gears provide greater wheel speed while allowing the engine to run at lower revolutions. After leaving the gearbox, power travels through the drive shaft toward the differential. From the differential, power is transferred through the axle shafts to the wheels. The wheels then apply force against the road surface, moving the vehicle forward. Now that we've seen how power flows through the drivetrain, let's take a closer look inside the gearbox itself and examine the components that make gear changes possible. The first component is the input shaft. The input shaft is directly connected to the clutch and serves as the entry point for power coming from the engine. Whenever the engine is running and the clutch is engaged, the input shaft rotates and transfers that rotational energy into the transmission. Next is the countershaft, sometimes referred to as the lay shaft. The countershaft receives power from the input shaft through a fixed gear pair. Mounted along the countershaft are multiple gears of different sizes, each corresponding to a specific gear ratio. As the countershaft rotates, all of these gears rotate with it, making it a central component in the transmission of power through the gearbox. The third component is the output shaft. This shaft is responsible for delivering power out of the transmission and toward the drive shaft and differential. Unlike the gears on the countershaft, many of the gears mounted on the output shaft are free spinning. They rotate independently until a gear is selected. The final components are the shift forks and selector rods. They rotate freely on needle bearings, and they don't rotate with the output shaft unless synchronized. Together, these components work as a coordinated system. Power enters through the input shaft, passes through the countershaft, flows through the selected gear pair, and exits through the output shaft. One important feature of this design is that all gear pairs remain in constant mesh with one another. This means the gears are always engaged tooth to tooth and continuously rotating. Now that we've seen how the gears are arranged inside the transmission, an important question arises. What makes them different and of great use? The answer lies in something called torque. Torque is a twisting force that causes an object to rotate around a pivot. To understand how this works, let's take a closer look at torque and how gears influence it. To understand how a gearbox changes torque and speed, let's begin with a simple set of gears. In this first example, both the driving gear and the driven gear are the same size. Because both gears have the same number of teeth, the gear ratio is 1:1. For every rotation of a driving gear, the driven gear also completes one rotation. This means the output speed remains the same as the input speed, and the torque remains essentially unchanged. This arrangement is often referred to as direct drive. It provides a balance between speed and efficiency because neither torque nor speed is being significantly altered. Now, let's look at a different gear arrangement. In this example, the driving gear is 5 times smaller than the driven gear. As the smaller gear rotates, it must complete 5 revolutions to turn the larger gear once. This creates a gear ratio of 5:1. The output gear rotates more slowly, but the torque increases significantly. In other words, speed is sacrificed in exchange for greater twisting force. This type of gear ratio is ideal when maximum pulling power is required, such as when starting from a standstill, carrying heavy loads, or climbing steep hills. In a vehicle transmission, this behavior is similar to what occurs in the lower gears, such as first gear. Now, let's reverse the arrangement. This time, the driving gear is 5 times larger than the driven gear. For every rotation of the large driving gear, the smaller driven gear rotates 5 times. This produces a gear ratio of 1:5. The output speed increases significantly, but the available torque decreases. This arrangement is useful when the vehicle is already moving and requires less pulling force. Instead of maximizing torque, the goal is to maximize speed and efficiency. Gearbox continuously takes advantage of this relationship, selecting different gear ratios to provide the right balance of torque and speed for the driving conditions. So far, we've seen how different gear ratios affect torque and speed. But one important question still remains. How does the transmission actually select a gear? The answer lies in the synchronizer system. It's the system that selects a gear. The synchronizer system is located on the output shaft and is responsible for connecting the desired gear to the shaft whenever a gear change is made. Let's look at the components that make this possible. The first component is the spline section of the output shaft. These splines are machined directly into the shaft and provide a fixed connection for the synchronizer assembly. Because the splines and the shaft are locked together, they always rotate as a single unit. Mounted onto these splines is the synchronizer hub. The synchronizer hub is permanently connected to the shaft through the spline section. As a result, whenever the shaft rotates, the synchronizer hub rotates with it. Surrounding the synchronizer hub is the synchronizer sleeve. Unlike the hub, the sleeve is able to slide left and right while still rotating with the hub. This sliding movement allows the sleeve to engage different gears when a gear change is required. Controlling this movement is the shift fork. But we only have one problem. The sleeve and the gears move on different speeds, so they can't engage directly when the gear is being shifted. It may just spark in contact. So, to solve this, we include a synchronizer blocker ring. It is the part that helps synchronize the speeds of the hub and the gear. It uses a conical friction surface to match speeds and features straight, chamfered teeth that allow the outer sleeve to slide into perfect alignment without grinding. Together, these components form the synchronizer system. Now that we've explored the components of the synchronizer system, let's see how they work together during a gear change. We'll begin in neutral, where all gears are rotating, but none of them are locked to the output shaft. To select first gear, the driver first presses the clutch pedal. This disengages the engine from the transmission, temporarily interrupting the flow of power and allowing a gear change to take place. The gear lever is then moved into first gear. This movement is transferred through the shift rod to the shift fork. Once engagement is complete, the driver releases the clutch pedal. Power now flows from the engine through the transmission and into the output shaft through the first gear ratio. The same process occurs for the third and fourth gear. Finally, let's look at reverse gear. Unlike the forward gears, reverse uses an additional idler gear position between the driving and driven gears. This extra gear changes the direction of rotation of the output shaft. After the reverse gear is engaged, power flows through the reverse gear train, causing the wheels to rotate in the opposite direction and moving the vehicle backward. And that's how a synchronized manual transmission works. From transmitting power to changing gear ratios to selecting and engaging gears, every component plays a role in controlling how engine power reaches the wheels. Understanding these mechanisms not only helps us appreciate how vehicles operate, but also reveals the engineering that makes smooth and efficient driving possible. Thanks for watching, and I'll see you in the next animation.